So today let's look into the wave nature of electromagnetic radiations. So in 1870, James Maxwell, he suggested or he proposed that any charged particle that is moving under acceleration will produce both alternating electric as well as magnetic fields. And these fields are transmitted in the form of waves, and the waves are termed as electromagnetic waves, or you call them as electromagnetic radiations. Okay. So let's say I have an electron that is moving, or it is revolving around the nucleus. As we know, electron revolving around the nucleus is a charged particle that is moving under acceleration. So that electron which is revolving around the nucleus will definitely produce electric and magnetic fields according to Maxwell. As you can see in this figure, you have the electric fields which is represented by the green color waves, and you have the magnetic field that is represented by the blue color wave, and these electric and magnetic fields are propagated or they are transmitted in the form of waves, and that wave is termed as electromagnetic wave or electromagnetic radiation. And now this electric field and the magnetic field, these two components will be perpendicular to each other. That is, my electric field, if I have EF, that will be perpendicular to my magnetic field, let's say MF. Okay. And that's also very evident from the figure. If one of it is moving along the y-axis, say for example, if this is my y-axis and this is my z-axis, so if, and let this one be my x-axis, okay, so I can say that if my electric field is along the y-axis, my magnetic field would be along the z-axis or any other axis that is perpendicular to the electric field. And now the propagation of the wave, now these two, electric field and magnetic field, together moves in the form of a wave, and the direction of propagation of the wave will be perpendicular to both of these. Now it will be perpendicular to the electric field component as well as perpendicular to the magnetic field component. So these two are perpendicular to the direction of propagation. So this is what you understand from the wave nature of an electromagnetic radiation. Now these electromagnetic radiations, as you know, they're waves. Now we have other forms of waves like our sound waves, for example. They require a medium to travel, right? They don't travel through vacuum. So unlike these waves like the sound waves that require a medium, my electromagnetic radiations or these electromagnetic waves, they usually do not require a medium and they can travel through vacuum. So that is the second point about electromagnetic radiation. So they can travel through vacuum. Okay, now there are certain terms or parameters that are associated with a wave. So let's consider a wave that is moving here. We have the green color representing a wave. Okay, now what are the different parameters or terms that are associated with this green color wave? So if you see that every wave will be having an uphill and then a downhill, right? So it starts from this position, it moves up, then it goes down and comes back to the same black line. The black line you see is the rest position of the wave, and it moves up and down along this rest position. This wave moves. Now from here to here, that is, it has from the starting position on the black line, it has moved once up, then it has moved down and it has come back to the black line again to the rest position. So this whole region from this point to this point, comprising of one uphill and one downhill, that can be considered as one wave. Okay, that is one wave. Now again from here to it goes up, comes down and again goes back to this rest position black here. So this distance between this point and this point, comprising of one uphill and one downhill, that can be considered as my second wave. So together they are continuously moving. Okay, now the uphills that you see, or the top points that you see for every wave, this topmost point of every wave is called as the crest of the wave. And the downhills or the depressions that you see, like this point or this point, the bottom portions or the depressions are called as the troughs of these waves. Okay. Now the distance, the total distance that is starting from this crest point to the trough point, this whole distance is called the height of my wave, which can be maybe h. And now half of that, that is from the rest position to the crest, or this distance from the rest position to the trough. This distance is a, or it is amplitude. The amplitude of the wave will be half the total height of the wave. That will be distance from the rest position to either the crest or from the rest position to the trough. Now, the distance between two crests. I have a crest here for my first wave, and then I have my second wave having a crest here. So this distance between the two crests of the waves correspond to their wavelengths, and or it can also be the distance between two troughs. That is, I have a trough here, I have a trough here. So this distance between them can also be the wavelength of the wave. The distance between two crests or two troughs are given by the term wavelength, that is represented by the Greek letter lambda. Okay, and since wavelengths, it is length, so its SI unit would be in meters, or I can say maybe in centimeters also. Okay, now I have the next term that is associated with a wave, which is the frequency of the wave. So frequency corresponds to the number of waves that pass through a given point in a given period of time. You fix a point and you fix a period of time, say maybe 10 seconds or 20 seconds, you fix a period of time and you fix a point, and how many waves pass through that point in that given period of time. That corresponds to frequency, which is represented by the letter nu, and frequency nu is 1 by time. It is the inverse of time. It is the number of waves that pass through a given point in a given period of time, represented by nu, which is 1 by time. So obviously 1 by time means it can be second inverse as its unit, or the common unit for frequency is hertz. In remembrance of the scientist Hertz, this frequency is given the unit hertz, which is represented by Hz. So now the next term that corresponds to or that represents a wave is the period of a wave. Now what is the period of a wave? Period of the wave corresponds to the time it takes for a single wave to pass through a given fixed point. You fix a point, and what is the time it takes for a wave to pass that point for a single wave? That is, this one single wave, in what time will that wave, that single wave, pass through that fixed point? And that is called period, and frequency nu can also be written as inverse of period. This is inverse of time, or it can also be the inverse of period, because period corresponds to the waves, the time it takes for a single wave to move, and frequency corresponds to number of waves that move in a period of time. So they are inverse of each other. Okay. And the last term that corresponds or that represents a wave is the wave number. Wave number, it is the inverse of wavelength, and wave number is given by the represented as nu bar. Nu is frequency, but nu bar corresponds to wave number, and this wave number, it is the inverse of wavelength 1 by lambda. Lambda is wavelength, and nu bar, wave number, is the inverse, or it is 1 by lambda, and it is the number of wavelengths per unit length. So if I have unit length, and how in that unit length, how many wavelengths are there? So that will give rise to my wave number, and it is usually given in the SI unit of centimeter inverse or meter inverse, but most commonly it is in centimeter inverse, nu bar. Okay. Now my electromagnetic radiations or my electromagnetic waves, they are also waves, so definitely some wavelength or frequency will be associated with those waves, right? Now the radiations or the waves that are emitted from the charged particles, they do not have the same wavelength or the same frequency. So the waves emitted by these charged bodies that are moving will be having different wavelengths and different frequencies. And depending upon the range of frequencies or the range of wavelengths they exhibit, these waves can be classified or grouped into a spectrum called as the electromagnetic spectrum. It is for the electromagnetic waves exhibiting different wavelengths and different frequencies. And these regions in the electromagnetic spectrum, they are given different names based on the wavelength and based on the frequency. They are given names like the radio waves, microwave, infrared, visible region, ultraviolet region, then we have the X-ray region, and finally we have the gamma rays region in our electromagnetic spectrum. So my whole electromagnetic wave that is coming out of a charged particle can have different wavelengths or different frequencies, and correspondingly I can have a whole spectrum like this, starting from my radio waves with the highest wavelength. So if I consider in the decreasing order of wavelength, it goes from radio waves, micro, infrared, visible, ultraviolet, X-rays, and lastly we have the lowest wavelength ones, which is my gamma rays. That is why here you can see the waves are longer, so they are having longer wavelengths. But as you move towards the gamma rays, my waves get shorter and shorter, and they have very low wavelengths in terms of meters. These values are written. Now if I talk about the frequencies, now this is the increasing order of the frequencies in hertz. So radio waves have the lowest frequency, and as you move forward and as you reach gamma rays, they have very high frequencies. Okay, and it is this visible region that you see, it is only a very small portion of my electromagnetic spectrum. This whole spectrum, a small region corresponds to the visible region that we see with our naked eyes as the visible light, which can be split into our VIBGYOR, violet, indigo, blue, green, yellow, orange and red. So this particular small portion of my whole electromagnetic spectrum is the visible region that we humans see. Okay. Now these waves, electromagnetic waves, when they are moving in the vacuum, they travel with the same speed, and they travel with a speed of light, that is 3 into 10 power 8 meter per second. So if the speed is represented by c, it is 3 into 10 power 8 meter per second for an electromagnetic radiation or an electromagnetic wave in vacuum travels with a speed of 3 into 10 power 8 meter per second, irrespective of what wavelength or what frequency the wave is holding. Let it be any wavelength or any frequency, let it be any part of the spectrum. Maybe it may be in the radio waves region, or the wave may be in the gamma rays region, but still all the waves, electromagnetic radiations in vacuum travel with the same speed of 3 into 10 power 8 meter per second. And now using the speed as a constant, I have a relation that relates my wavelength and frequency. That is, my speed of the wave c can be written as a product of wavelength and frequency. My speed is nu into lambda, nu times lambda, that is frequency into wavelength. So this is an important equation that comes under the electromagnetic wave nature of electromagnetic radiations. And that is all about electromagnetic radiations. I hope you have understood whatever has been discussed today. Thank you so much.